Hello and welcome back. You are watching BitLearn, where I make deep tech simple and easy to learn. I share the knowledge I have gained from years of building real products so that you can go beyond learning and you can start creating your own tools, products, and maybe businesses of your own. So let's get started. You're on episode 5 of Learning C. So far in C programming, we looked at a high level overview of what are the constructs and what are the commands that are available. So we looked at control flows, we looked at functions, we looked at recursion. What else? We also looked at looping, a lot of different things. So if you have missed any of these episodes, make sure you go back and watch them. So this is episode 5 and we are going to look at how do we organize complex data. Okay, let's get into it. So programming often looks deceptively simple in the beginning. You write a few variables, maybe print something to the screen, perform some arithmetic, and everything feels under control, right? But the moment you begin working on something real, something that must model a human or a game character or a student record, everything, you start hitting a wall of complexity. So let's look at it. How do we deal with it? Real world information rarely comes as just one neat little number. It doesn't come like that. It comes as a cluster of related values that must be treated as a single unit. So if you look at a person, he has a name, he has an age, a height, all of these are related to the person. A product, it has a price, barcode, manufacturer, or a game character, it has inventory, statistics, attributes, all of these things. These pieces of data do not just describe the object, they actually belong together. So I am a person, my height, name and height as individual attributes don't mean much. You put them all together, it kind of describes me, it belongs to me. So before you can build anything meaningful in C, you must learn to answer two essential questions. How do we bundle related data together so that it behaves like one logical unit? And how do we ensure this bundled information doesn't disappear when you turn off your laptop or your computer? How do we make sure it persists? It is still available even when your program is not running. So these are the two things we'll touch upon in this episode. So we will go through the exact tools that C provides to solve these problems. They are not just features that transform the way you think about programming itself. So let's look at the problem of data that is scattered like paper scraps. We begin with something very simple. Suppose you want to store information about one person. If you are new to C, your instinct might be to create multiple variables. You create a variable to hold a person's name, a variable to hold his age, height, and so on. The issue is very subtle but enormous. To you, these values describe one person. You know that, okay, this height and this age and this name, they belong to this person. You know that. But to C, they are just unrelated memory locations floating around independently. Nothing binds them together. The computer does not know that. The name, age, and height, they all belong to the same entity is something that the computer does not know. So this kind of disconnected data quickly becomes unmanageable. Suppose you have 100 people's data around, right? You're going to have 100 variables of ages, names, everything thrown around. How do you make sure that this age belongs to this person? How do you make sure that this name actually belongs to this person? You want to put it all together. And as your program grows, this complexity really multiplies. Now, you don't have just a few variables, you have like hundreds of them. And the connection between them lives only inside your head. You know that it's all related. So we need a way to have a single object that holds all of these values as one meaningful whole unit. So that basically is a structure. So C offers something called as a structure. This lets you group variables of different types under one umbrella. So it's essentially a custom-made data type that you designed yourself. Think of a structure like an identity card, a contact card, or a visiting card. Instead of scattering your details about your name, your phone number, your business around randomly, what you do is you have a structure which brings everything together onto one contact card, which you can just hand it to somebody when you go there. When you meet somebody, if they ask for your contact information, instead of giving them different scraps of pieces of information on different sheets, what you do is you have a single contact card or an identity card which you just hand over. So that is basically a structure. So before you create such a unit, you need a design, a blueprint. If you are printing a visiting card, you need a design. Because every time you don't want to start thinking about, okay, how do I build this structure? Where should the name be? How should the age be? No, you come up with a template and you just use the template to print as many cards as you want. The structure is that. structure does exactly that. It's a blueprint of your data structure. So if we take this example of a person, there is a name, there is a age, and there is a height. So this can be a template. Whenever we are creating a person's details, it's going to have these three things: name, age, and height. So that's a template. You create a struct called person, have a character array to hold names, maybe an integer to hold age, a float to hold his height or something. So this definition really doesn't allocate any memory. A struct, it merely tells C that whenever I say struct person, I want you to prepare these three fields for me and put it together. So you have basically invented a new data type. Just as int represents whole numbers and float represents decimals, struct person now represents the concept of a person. So let's look at creating actual data. Once the blueprint exists, you can create real variables from it. So you can just say struct person p1. It will create all these three related variables to you and give it to you in a data structure called person p1. So this is like printing an actual physical identity card based on the blueprint or template you created. You created a visiting card design, right? Now you can use that design to print as many cards as you want. So similarly, p1 was a person. Now P1 exists in memory with all these fields readily created to store information. That is how a data structure works. Now let's look at storing values inside the structure. So C provides a very simple readable syntax using the dot operator. So we created a person called P1. If you just look back at the previous slide, we said struct person P1. So that created a structure to hold a person's details, name, age, and height, and we gave it a name called P1. Now if you want to set the P1's age or the person 1's age to 20, you just have to say P1.age equals 20. Similarly, for this person, if you want to set his height, you just have to say P1.height is 5.8. So this design is very intuitive, clean, and it kind of scales very well. Suddenly, instead of juggling dozens of variables, you handle just one object, P1, with multiple fields in it. And you can just pass P1 around. It will go with all its attributes. It will go with its age, height, name, all of those things, they go together. So they belong to each other. So if you have 100 people, you store them as an array of structures, not 300 individual variables. You can have an array of persons, which basically gives you an array of P1, P2, P3, P4 up to P100, and each person has age, name, and whatever, height, whatever you define. So C structures make your code kind of reflect reality. A person in real life has a name, he has a height. So the C structure is also similar. It helps you to build that reality. So this is not something C does by default. And next let's look at the memory behavior of structures. One important thing to understand is how memory works with structures. Each member of the structure gets its own dedicated space. So if a structure, the person structure we used, if it has a name as an array, an integer called age, and a float called height, C allocates storage for all three of them. A structure size is essentially the sum of the sizes of all its members, the name, the height, and the age, right? So this makes structures perfect for storing complete multi-field objects where all members are needed simultaneously. So when somebody asks for details of a person, he's not going to ask for each individual item, say give me person's name, give me person's age, height. No, he's basically going to ask you for a person. And what you will do is you'll just pass the person object P1, the structure, to whoever asked, and he gets all the related data along with P1. But sometimes you don't need all members at the same time. This is something interesting. So this is where C offers something entirely different. This is called a union. So union is where memory is really low. Let's look at how union is useful for us. A union looks almost identical to a structure. Instead of struct, you call it as a union and you start defining the same structure. If we take the person as an example, you can still define the same structure as name, age, height. But there is one key difference between a union and a structure. A structure gives each memory a separate place to store its information. A union forces all members to share the same memory location. What is this? Let's look at it. How does it even work? So only one member can hold a meaningful value at any time. So if in your program, for some reason, you know that whenever I store a person's name, I don't need his age and height, or whenever I store his age, I don't actually need his name and height, all those variations. So basically, if you know that you can store only one piece of information at a time, then you can basically define it as a structure. So that way, what will happen is, think of a structure as a tray with three compartments, one for keys, one for wallet, and one for sunglasses. So it's a small single box. If you put a wallet inside, you can't put your sunglasses into it because it's going to crush your wallet. So whichever item you store last is the only valid one. Now let's break it up a little bit. So why do we even need a union? To save memory. If you know your program will use only one of the several possible data fields at a time, a union can drastically reduce memory consumption. So if we look at our example of a person, 32 bytes was a name, 4 bytes was the integer for age, 4 bytes was a float which was for height. If you know that you are going to use only one of them, what C will do is, if you declare this as an union, it will allocate the largest value you will ever store using a union. In our case, we are going to store 32 bytes, which is a name. So it will allocate only 32 bytes. So using 32 bytes at any point in time, you can store any one of the variables, right? If you want to store a name, it is 32 bytes. It fits very nicely into that because it has allocated memory. If you are going to store an integer, it is 4 bytes. It fits very nicely within the 32 bytes because it created 32 bytes for you. Similarly, a float. So the entire union occupies only 32 bytes, the size of its largest member. The rest are all stored in the same exact space. So in contrast, a structure holding these fields would need 40 bytes because it reserves separate memory for each member. So in large arrays or kind of memory constrained environment like a small embedded system, an IoT device, this difference is huge. But the catch is you will be able to use only one element at a time. So the trade-off. Unions give memory efficiency but at a price. Only the most recently assigned member is valid, the others do not exist. Accessing any other members will lead to garbage values. Unions solve a very specific problem. Situations where you have several possible types of data, but you need only one of them at a time. So that's where it's extremely useful to have a union. So now a new problem appears. What is the new problem? You turn off your computer, all your data is gone because your memory is now cleared. Structures and unions kind of help us organize data, but everything they store lives in the computer's RAM. And the RAM is temporary. It is wiped clean. The moment your program stops running, it's wiped clean. So this creates a new challenge. How do we make our data persist after the program ends? This is especially important when you're creating programs such as games that need to save files, database, configuration systems, sensors, all of those things. So C solves this through a facility called file handling. So the file handling, this kind of gives your data a permanent home. File handling is the process of taking structured data and storing it permanently on disk, on a hard drive or a SSD, so that it survives the power loss and program termination. So the metaphor here is kind of perfect. If a structure is your contact card, a visiting card which you hand over to people, then file handling is the file cabinet. You store it in. So once you receive somebody's contact card, you put it in your file cabinet. It's always there. You open the filing cabinet, you can pull it out. So that's how it is. So your program can close, the machine can restart, but the file will still remain. So here is the 3-step model for file handling. Every file operation in C follows a strict predictable sequence. You open the file just like your filing cabinet, you read or write data, and then you close the file. The filing cabinet, you open it, you take out your contact card, then you do whatever reading or writing you want to do, put it back, close it. So these are the 3 steps: open, read, write, close. So that's detailed out here on the slide. You can take a look at that. There are some special modifiers when you're opening a file. So the mode of the file basically will decide what you can do with the file. You opened your filing cabinet. If you said the mode was write, then it allows you to write a new contact card, put it back. If you open the file as read, then it allows you to only read. It is read only. Append allows you to not modify any of the existing data, but you can add something to that. R plus will allow you to do read and write, both of it. So that's how a file pointer works. You get a file pointer to your filing cabinet, and using the file pointer, you can do read, write, append of data types. We'll go into the details of that a little later. Now let's look at reading or writing data. This is where your data flows from memory into storage. So fprintf, very similar to the printf we looked at. Now this time it will do a printf into the file. Just like we used printf to do a hello world, you can do fprintf to a file pointer. It will write the hello world to this file that is created. So similarly, we have fputs, which is which will put an entire string, fwrite, which will do binary write, and so on. You can take a look at all the details in the reference sheet. You can also download some of these notes out in the description below, and you can look at that. Then most importantly, closing the file. So it is very important to call fclose on a file pointer. Otherwise the file cabinet, the analogy we talked about, it will never be closed and it will be open. So that creates lots of issues. If you don't close it, then basically you start getting leaks, you may get corrupted files, you get all sorts of issues. So closing the file, it ensures that data is actually flushed to the disk. Flush is basically pushing any pending data to the disk. The file pointer is released and the system resources are freed. This basically closes the file cabinet for you and you have your clean disk again. Forgetting this is like leaving the file cabinet open. It is very risky and unsafe. It creates lots of problems. Then let's look at reconstructing your data. Once you have written a structured data into a file, your program has the capability to continue remembering the data you gave it. The next time it starts, you can open the file, read its contents back into the same structure that you created, and your application can resume where it left off. So that is how files are very useful. So let's quickly try to bring it all together. By now we have learned two of the most important concepts in building real applications in C. Structures and unions, they allow you to model real world objects. File handling, it ensures your information kind of stays or survives beyond the lifespan of a program. All of these together, they upgrade your programs from temporary short-lived experiments into meaningful applications that can organize data, store it safely, restore it, and kind of behave predictably. So this is the point where C begins to feel very powerful in your hands. So far we have covered quite a bit of C in the last 5 episodes. We looked at control structures. It told us how to decide, how to make decisions. We looked at arrays. We looked at a lot of interesting capabilities of C. This one in episode 5, we basically looked at how do we organize complex data, how do we store and retrieve data. So this combination is the foundation of many real software systems. So at this point, you have the awareness to build a really useful C program. I have not gone into fine details of every line of C. I have just given an awareness. So this is a good time to pause and start writing your own programs. While we continue the series, make sure you do some hands-on work, get your hands dirty, build something in C. So meanwhile, I hope you're enjoying the episodes. Please do subscribe, like the video, leave some comments, and do come back for the next episode, and do keep experimenting with C. Thank you for watching.